Okay, we're going to look at a couple of questions just real quick here. We have a table of elements over here on the left side. You can see that we have time in terms of seconds, and we have velocity in terms of meters per second, and they only give us 3 points. And then below that, they say when t is equal to 1 second, the position of the particle is 10 meters. So when t is equal to 1, we are at 10 meters along the x-axis. Now it does say at the top that the acceleration is positive on the interval from 1 to 6, and then they want us to explain why the position of the particle must be greater than 24 meters at time t equals 6 seconds. Now the fact that it says that the acceleration is positive from 1 to 6, that means the velocity would be increasing on that interval. So we're really just looking at the interval from 1 to 6. So we can basically ignore the last point right here. We can just cross it off. And so what's really important here is that the velocity on that interval is increasing from 3 all the way to 4. So we can say for sure that v of t is greater than or equal to 3 on that interval. And again, the units are going to be meters per second. So I'm going to put m over s. So on that interval, we know that the velocity is at least 3 meters per second. And you can see we're going from t equals 1 to t equals 6. So that's 5 seconds. So if you travel 3 meters per second for 5 seconds, then we know that we've traveled more than 15 meters. And if you started at 10 meters and you traveled more than 15 meters, then at t equals 6, you must be greater than 25 meters. So we know for sure that the position is greater than 25 meters. So if it's greater than 25 meters, then it must be greater than 24 meters at that moment in time. Now I'm going to go ahead and write that in kind of like a sentence. I know that the position of the particle when t is equal to 6 is going to be the starting position when t is 1 plus all the changes, and this is going to give me 10 plus. And for this part right here, we don't have the position function because what I would like to put is x of 6 minus x of 1. But I don't have the position function. Even though I know x of 1 is 10, I do not know x of 6. But what I do know is I can figure out the changes based on the fact that I know that the velocity on that time interval is greater than or equal to 3 meters per second during those 5 seconds. So 3 meters per second times 5 seconds. When I multiply that together, I'm going to get 15 meters. So I can replace that with a 15 meters. But because the velocity was greater than or equal to 3 on that interval, I know that the position when t is 6 should be greater than or equal to this amount. And of course, this is 25, which is clearly greater than 24. So that's kind of another way of writing it. We're kind of putting it in a sentence here. So this is a little bit better work. And this is kind of the solution that the answer key would have on the AP test, something like this. And again, the reason why the velocity was greater than or equal to 3 on that interval was because the acceleration was positive on that interval. So that meant that the velocity was increasing on that interval. So the velocity was greater than or equal to 3 on that entire interval. And we can see that it started at 3 and it ended at 4. So it increased from 3 all the way to 4 on that interval. All right, this is our second example here, and it's actually our last one. We have a table of elements that gives us the velocity at different moments in time. Then it says what is the smallest number of instances at which the acceleration could be 0 on this interval, so the interval from 1 to 9. Now there are a couple of ways that you could look at it. You can see that the velocity is increasing until this point right here, and then the velocity decreases until you get to this point right here, and then the velocity starts increasing again. So common sense tells you that if our acceleration was positive and then changed to negative, well, it must have passed through 0 at some point. And same thing over here, our acceleration can't change from negative to positive without also going through 0. So common sense kind of tells you that there are probably going to be at least 2 times on that interval where the acceleration could be 0. Now, we're not allowed to use just basic common sense. What they're looking for here is some kind of math reason. So I've kind of highlighted those 2 reasons. You can see one of them is in purple and the other one is in yellow. And so we're basically going to use the mean value theorem here. And since the slope of the tangent line is 0, it's actually called Rolle's theorem. It's a special case. Whenever your tangent slope is 0, it's called Rolle's theorem. But remember, Rolle's theorem is the mean value theorem. It's just a special case of it. So using Rolle's theorem, or mean value theorem, we're going to say that because the slope of the secant line is 0, from t equals 2 to t equals 4, then there's going to be at least one spot inside that interval where the slope of the tangent line is also 0. And the slope of the tangent line would be the acceleration. And using similar reasoning from t equals 5 to t equals 8, you can see the slope of that secant line is 0. So we're guaranteed at least one spot inside that interval where the slope of the tangent line is also 0. And again, the slope of the tangent line would be the acceleration. Now, we do want to keep in mind the two conditions in order to use the mean value theorem is that your function must be continuous on the closed interval. So for example, it must be continuous from 2 to 4, and that's for the purple one. And we must also be differentiable on the open interval. So we must be differentiable from 2 to 4. So in order to use mean value theorem on this interval from t equals 2 to t equals 4, both of those conditions must apply. I think the missing component for this question is it's supposed to say that the velocity is differentiable on the entire interval from 1 to 9. Again, in order to use the mean value theorem on this interval right here, our function must be continuous from 5 to 8. So that's going to be a closed interval. And we must be differentiable on the open interval from 5 to 8. So you'll see when you do this question on your homework, it does say at the top that the function v of t is differentiable on the entire interval. So of course, if the function is differentiable on that interval, it's also going to be continuous on that interval. Now here's an example answer solution, and it starts off with the fact that the function was differentiable. So it needs to tell you that. It needs to tell you that the function is differentiable. So if it's differentiable, then you know for sure that it's going to be continuous. So that means that you can use the mean value theorem. So here we're saying according to the mean value theorem, it says v prime is equal to 0, that's the acceleration, somewhere on this interval from 2 to 4, and also somewhere on the interval from 5 to 8. So in that case, we know that the acceleration will equal 0 for at least 2 values of t. So this is just a sample answer. Remember, for each interval, we need the function v of t to be continuous on the closed interval. So that would be, in this case, from 2 to 4. And we also need it to be differentiable on the open interval. So again, from 2 to 4. But if we have a function that's always differentiable, then we know it's going to be differentiable and continuous everywhere. So all you really need to do is just state the fact that it's differentiable, and you're kind of done with all the conditions that are required. Of course, we would need the same conditions going from 5 to 8, but again, this covers it right here. Just saying that v is a differentiable function of t, and that's usually given at the top. So we're assuming that that was given, so that means that we can use the mean value theorem here. Remember, your answer doesn't need to be exactly like this. You can put it in your own words, but this is a good sample answer.